Log on, tune in, find out. Another good idea from Cambridge.
And he tell us about Hilbert schemes of singular planes and HOMFLY homology of them.
Okay. Well, there's two basic things in this talk: curves and knots. There are some curves. All curves will be locally planar, reduced over C. And here are some knots. Okay. The way you get from this picture to this picture, did I draw that right? Is pick a point, draw a small ball around it. This ball is an S3. Its intersection with the curve is a circle or perhaps a collection of circles. And so you get some circles in the three-sphere. Okay. Some sort of basic, there's an extremely classical correspondence and some basic facts about it. If your singularity was given locally by some function, and let's say the singular fiber in question is over the origin, so here's C, here's C2, here's singular fiber over 0, then nearby, since this is reduced, there are smooth fibers, and if you take this S3, then it maps. So you just, this function maps it down here, and if you take a different color maybe. If I take a point here, its free image is this. Its intersection with this ball, so the ball inside, is called the Milnor fiber. As you vary around the circle down here around the origin, you can push these out to the boundary, and then you get a fibration S3 minus the knot goes to the circle, and the fiber is this F. There's an invariant which is nice to think about, which is you look at the cohomology of F, and you look at this monodrome reaction, and you consider this its characteristic polynomial. And the starting point of this talk is a theorem proved by Campillo, Delgado, and Guzenzad. So Guzenzad is one person. Which says, so this is sometimes called the zeta function of the monodromy, which says you could recover the zeta function of the monodromy from the ring of functions on the curve. Well, the way I'll write it here, look at the ring of functions on the whole on the whole space at the origin, and you write this. F is the function cutting out the singularity. And what this means is that I stratify this space by this function, I mean by this intersection number, and I compute, so by definition, this is the sum over integers k of the Euler characteristic of the locus in C xy, which intersects f in, so t to the k times k points. I mean, intersects it at k points at the origin. Okay.
I'm going to throw out f here.
So I make the convention t to the infinity equals 0. Well, anyway, they do. So they proved this theorem by computing both sides by resolving. But let me instead just mention some heuristic reason to believe it, which is that if instead of having written, instead of having a curve, so I'm going to take the point of view that this is really a curve over the formal punctured disk. I mean that this thing is a curve over the formal punctured disk. And if instead of having that, I had a curve over a finite field, and if instead of having had monodromy, I would have had Frobenius, then the analogous thing would have been equal to the sum t to the k times the number of points over fp to the k, well, let's say over fp, of the kth symmetric power of that curve. And so I'm now just going to brutally replace, I'm going to go back to this situation, and I'll brutally replace this by an Euler characteristic. And I mean, the Euler characteristic of CQ. So I look in the algebraic closure, and I look for CQ valued points. And what are CQ valued points? Well, they're just sections of this, or in other words, k sections of the curve. And a k section of this curve over this formal punctured disk is, well, it just looks like this, right? It's, I pick k points on each fiber. And such things are just precisely the zeros of the polynomials which intersect in k. So that's why you might believe that formula. But anyway, they prove it by actually computing. Okay.
Is this proof of motypic integration type thing? Like they blow up and write some motypic integral that computes both sides, or is it something else?
So one side you compute with, this Ocampo formula, which in some sense is some of the motivation behind the formulas written down for motypic integration. The other side is a huge mess. I don't know how they computed it.
It looks as a dual formula because they use not arcs, but
Okay. So I'm going to try and extend this by making a series of conjectures. And first I'll have to talk about some other knot invariants. So a different name for this thing is the Alexander polynomial. And a different description of it is the following. You write a skein relation. What a skein relation? Well, I'll first write the skein relation. I'll tell you what it is. What this means is that if I have three knots, well, one of them will be a link at least, and if I have three of them, and which look the same everywhere except for some small neighborhood where they're related by where one looks like this, one looks like that, one looks like this thing, Then the Alexander polynomials are related in this way. And let me, so you also ask the Alexander polynomial of the unknot equals 1. That's not going to give you this. It'll give you this up to some power of t in minus 1. But set that aside. So let me just give one example of what this means. So if I had, say, so if I said, if I wanted to compute the Alexander polynomial of 2 unknots, well, I'll just fill in the other pictures. And of course, that side's 0. Okay. So that's the Alexander polynomial. Then there's the HOMFLY polynomial. These are like 8 people who all apparently discovered this simultaneously. Their names are Host, Okneanu, Millet, Freud, Licorice, Yader, Pachitsky, and Trach. Well, the last two probably didn't do such a good job. Anyway, it's quite similar to this one, except there's one more variable. And for no apparent reason, I'm going to change t to q now. So, I choose this normalization. So I'll write the HOMFLY polynomial as p within overline. And then you have to choose its value on the unknot. And I'm going to make this slightly unfortunate choice, perhaps. Okay. Okay, that's the HOMFLY polynomial. It's, it's not clear there's any sort of definition. But it turns out it is, that there's a unique function on knots which obeys that cut and paste relation. Okay, and I'll need one more. Here's the other one. This one is called the HOMFLY homology. So I guess Kovanov, so this is the work of Kovanov, and maybe in Rosansky. But I'm going to take the definition from Kovanov's paper on Zergel bimodules. And the definition of this is that you start out with, first of all, you're supposed to draw your knot as a braid. Okay, what is that? It means you draw it like this. Anyway, there's the same number of strands at each slice. Okay, and then you know, it closes up on the outside. So.
They're not always three strands.
Okay. All right. Yeah, not always three strands. Yeah. Okay. So, and then you do the following thing. If there's n strands, okay, you write this. You write the polynomial in n variables. We'll call that R. And then you write Ri for the invariant part when when xi is exchanged with xi plus 1. Okay, and then you write Bi for the tensor product of R over Ri with R. And this is the tensor product as R bimodules. So R acts on the left and on the right, and here it acts the same way, and here it acts the same way, but here it, it acts on the left like this, and on the right by that way. And then you make some chain complexes. You write so there's one like this, and this one goes 0 to q squared r. By q squared, I mean, so this is a graded ring. Polynomial, I take the variables to have grading 2, and by q squared, I just mean shift the grading by 2. Okay, so this is one of these things, and this map sends 1 to xi minus xi plus 1. I'm not going to use any of this later on. I'm just writing it so that you know it's explicit. Okay, and there's another one that corresponds to the other thing. And this one goes the other way. This one goes 0 to bi to r 0. And this map is just 1 goes to 1. Okay. And what you're supposed to do with these complexes, you tensor them together. I mean, you tensor them together in a sort of obvious way. You look at your braid, and you see where the pictures that name the complexes appear. So, and then you tensor them in the order in which they appear. So in this case, I would write this 1, 2, and then I would write 2, 3, and then I would write 1, 2 again. And then when when you tensor them, you take the total complex. Okay. Now you have some big complex. Now you so if let's say my braid was called beta, then this is called the Rouquier complex of beta. And now I'm supposed to take its Hauschild homology. So that I take R beta tensor over R tensor R. And so what is this? Well, so I mean this is the derived sense or whatever. So this is where each time I had a term in the complex before, now I have this, a bunch of different vector spaces. Okay. And now I'm supposed to take, so this is, let's call this H8 Hauschild homology of R beta. And now, this thing had a differential, and so now I take the, with respect to that, and now I have a triply graded vector space, and the 3 gradings are, one is the polynomial grading. One is the grading from the Harshfield homology, and one is the grading from the complex. And the relation of this to the HOMFLY polynomial, which is written over there, is that if, the theorem that Kovanov and Rosansky prove is that this is in fact an invariant of the knot. And so let's call this, it's an H of this knot. And it has 3 gradings. And so the relation of the HOMFLY polynomial is that sum a to the I, q to the I, a to the j, negative 1 to the k, the dimension of this h, I, j, k is the HOMFLY polynomial. Okay. So I'm not going to make any actual calculations with that, but somehow several people asked me whether or not this is an actual thing, so that's what its definition is. Okay, now I turn to Hilbert schemes of points on curves. So for C, for x any space, I write xn. Say x is a quasi-projective algebraic scheme. For subschemes of x, there's Hilbert scheme of points of length n. Zero dimensional. Okay. And for C, a smooth curve, this is just a symmetric product. Unordered n tuples of points. Okay, and for singular curves, it's something more complicated. Just illustrate that with some pictures. So I'll take 3 singular curves, and in fact I'll only take their germs at one point. Well, one of them is not going to be singular at all. Just a smooth curve. So okay, let's see. One of them will be a smooth curve, and I'll look at its germ at this point. One of them will be a nodal curve, and one will be a custal curve, and I'll look at its germ at this point. This is the cusp, this is the usual cusp. And now I'll write the various Hilbert schemes. Okay. And so in this case, they're all points. In this case, Hilbert scheme of 0 points is always a point, so I'll put that here and here. Hilbert scheme of 1 point at the origin, well, you always have only the maximal ideal. So there's that point again. 2 points. In both cases, they're sort of planar curves. So subschemes of length 2, you can have any one of them because it eats up the whole. As soon as you have a singularity of the whole tangent space. So in both cases, it's a P1. And when you start to have 3 points, well, here it turns out, you can either stick out sort of more in this direction or more in that direction. And what that turns out to mean is you have 2 P1s to intersect with a point. But this guy, he's going to be P1 again.
And is that intersection the square of the ideal? That's a limit through thing. Is that inside that guy?
What do you mean?
Well, you said they stick out, right? But so in 3 points in the plane, they're all either along a curve, or they're the fat point?
Yeah, it's this one.
And it's that one.
Yeah, sure. I mean, that's the one that's the limit. Okay. 4. So this one will turn out looks like that. This one's just P1 again. Anyway, you can see the pattern. It continues forever. Okay. And what I do with these things, is I take generating functions of, I take generating functions out of them. So I look at, so for C now, C is always a singular plane curve now. I look at the sum Euler characteristic of the n Hilbert scheme, Q to the n. And let me say a few things are known about this series. The first is by a theorem of Rahul and Richard. This is a different PT. This can be written as a sum. So let me discuss the case where C is a complete curve. This can be written as a sum, but from H going from the geometric genus to the arithmetic genus of some numbers, some integers nh, times some constant polynomials, times some q to the g minus h, 1 minus q. Okay. And these are called the BPS numbers of the curve. But, what's really true is that there's a in certain good cases, there's a contribution of this curve to the BPS invariance of, some whole family of curves. I don't necessarily know if there's any actual meaning, any actual physical meaning to that. And there's one other thing I know about these, which is that if you look in the universal deformation of C, so there's a space, I'll call it lambda, and it's got a family of curves over it, over which the central fiber is C itself, and then there's some other fibers. And so inside of here, there's some naturally defined loci. So one will be the discriminant locus.
Are you now back to the case where this is a germ of a single?
No, this is a complete curve. It doesn't matter. The theorem is true either way. I mean, the way I'm going to state it in the case of a complete curve. Okay. So there's some discriminant locus, and that's the generic point of the discriminant locus. Curve has one node, and I'm going to call that the locus, the Severi locus, the G minus 1 form. And the whole thing I'll call, SG. And the next one, there's some locus where a curve has 2 nodes. And here, call this one. This is the name of the locus, not the name of the curve. And the theorem is that NH is the degree of SH. And let me just say one word about why that's true. I shouldn't have moved that up. Oh. So the point is, okay, so get this picture. Well, let's say, let's talk about this yellow locus. I'm going to consider two things. So now this is going to be a locus SH. I'm going to consider two things. Let's call this guy D0, D0, D1. These are chosen so that they're the complementary dimension of this locus, so this one cuts it transversely. And I regard those numbers as defining a function on this space. So at each point, you make those numbers by, taking the generating function of Euler numbers of Hilbert schemes, expanding it out, changing variables in this way, and then you get a number for that curve. So I'm going to compute, on the one hand, this integral. And H respect to other characteristics. On the other hand, I'm going to compute this integral. Okay. And, well, I'll argue in a second that these are equal. And what does that mean? Well, this one, by the theorem of by the theorem of Rahul and Richard up there, this only picks up contributions from the locus where the curve has geometric genus at least h. Otherwise, it doesn't contribute. And the number of times it hits that is precisely the degree of SH. Okay, so this one is equal to the degree of SH.
That's because NH equals 1 for...
Yeah, right. NH equals 1 for a curve with only nodes. Sorry, yeah. A curve with only nodes of geometric genus H. NH equals 1. That, you have to calculate that. Okay, and then as for this one, well, as you can see, there's no other curves of genus H sitting here because they're all sitting in this yellow thing. And so the only contribution is from the NH of the central fiber. This is NH of the original C. Now, why are these two equal? Well, this and this are each written in terms of the Euler numbers of the Hilbert schemes. So it's enough to prove that for sufficiently many of these Hilbert schemes, that the analogous integrals are equal. So I have to prove that. But of course, this is just the Euler characteristic of the the total space of the fiber. So now I have to make some sort of smoothness argument to say that the fiber over this is the same as the fiber over this. And anyway, you have to make some sort of smoothness argument, and that's the geometric content of this statement. I'm not going to discuss that, though. All right. So now I introduce a few more spaces.
I missed something. What was the Hilbert scheme of endpoints on C in this picture?
Where?
So this was deformation. You had that fixed C. This is the versatile deformation space. So how did we get to the C to the N, the Hilbert scheme? I just missed something.
So, are you asking what is the meaning of this?
I'm asking from that picture, where do we get the Hilbert scheme of C, of endpoints on C?
So over this, I take the family of curves. I take the relative Hilbert schemes,
Oh, you do the okay.
and then this is the one at that fiber. Okay. the smoothness argument isn't trivial. I mean, you have to say something. Okay. So a couple more spaces. I'm going to write C n plus m for a certain incidence locus inside here. And it's where I have one ideal sitting in another ideal sitting inside. So now I take C to be just the germ of a curve. So this is at one point. And M is the maximal ideal at the point. So I'll put I'll put a P here to emphasize that it's just at a point. Okay. And the n plus m, so the dimension C of I is n, and dimension I mod j is n. So I wish someone would tell me what the meaning of this incidence variety was. It's written down to make the next thing work. Okay, so now I can state the knot conjectures. So, okay, that's good. So this is with, let's say, Blomkopf. And so you form the following series. So this is some generating function of Euler numbers of these things, and the conjecture is that this equals the HOMFLY polynomial What's wrong with minus 1 at the n squared? Well, of the link of C at P. So that's one conjecture. Mu is the Milnor number of the singularity. And conjecture 2, much of the same form, the one is with Alexei and Jake Rasmussen. And I'm going to write, again, something like this. I mean, this means virtual Poincare polynomial. And this is this generating function of dimensions, so it's the generating function of dimensions of triply graded homology.
This nesting is supposed to be equivalent to the number of generators?
Yes. So, I mean, Yeah, so
Are you going to explain that, or is this a new formulation?
it's identical to the old one. So if you want to think about it in terms of number of generators, this is just saying I pick something in I mod mi. And so that's a Grassmannian in the number of generators. And this -1, the Euler characteristics of Grassmannian summed up. If you sum that up, that looks like 1 minus a squared to the number of generators. Okay. But somehow, this one looks nicer than this one. And this is supposed to be this triply graded homology. Okay. Is there any questions about the statements?
Did you say what KCP was?
Yeah, virtual Poincare polynomial in T. So I should mention that it is not my opinion that it's relevant that it's virtual. I think those things are all pure. But certainly all the calculations we've made have been virtual.
You think those are paid by Apple?
No. They're no, not to me. I don't know whether or not they all sit in the motive generated by the affine line. That's probably true, but I don't know. I don't know a ton of that. Okay, so let me say something about the evidence for these. So conjecture 1 is, so first of all I should say that, setting A equals -1, these specialize to the theorem of Campillo, Delgado, and Guzenzad. So that's, and how does that happen? Well, over here, that's in the definition of the HOMFLY polynomial and the Alexander polynomial. And then the other side, if you go through this sort of alternating sign discussion I was having with Rahul, you'll see that it cancels out if there's more than one if m mod mi is, if I mod mi is a dimension bigger than 1, because you got sort of alternating signs and these binomial coefficients get to cancel. So you're down to sort of ideals with one generator, which is just back to functions on the curve. Okay, so the evidence, so 1, it specializes. 2, these things, it's not evident from the way they're written, but they're invariant under Q goes to 1 over QC, or Q goes to -1 over Q in this one, which is supposed to be true for the not polynomials. 3, this one, conjecture 1 is true. It's true for singularities of the form x of p equals y to q for pq relatively prime, and a few more. By explicitly computing, one side, that side, and Jones has previously computed this thing. 4. So okay, now I talk about conjecture 2. Conjecture 2 is true in not so many cases. For x squared equals y to the n. It matches conjectures of the not theorists for x cubed equals y to the n. It's true for small values x to the a equals y to b, and whenever the knot theorists can compute this, we check it. And it's sort of true in the limit x to the n. I mean, in the limit is n. In the limit is like sort of x to the a equals y to the b as b goes to infinity. There's a paper with Gukov and Dunfeld and Rasmussen where they make a conjecture about what the HOMFLY polynomial, what the HOMFLY homology looks like in this limit. That conjecture, I mean, Jake has proven that conjecture, and it matches. On the other hand, if you look at what this is talking about, that limit, it's just Hilbert schemes of points on a thickened line, because you've sent this to infinity. And so that's kind of straightforward to compute. Okay. And now, I guess in the rest of the time, maybe I'll discuss a little bit how you compute on this side. So, I discussed the case x to the p equals y to the q, which means I'm looking at the ring of functions, this ring of functions, has a torus action by scaling t, and I'm just going to count fixed points. So what are the fixed points? Fixed points are monomial ideals. And these, you always enumerate in the same way. Here, so I'm going to draw this picture. 1 t to the p, 2p, q. And I go up to t to the q times p minus 1, because if I go up any more, then I'll have something which shows up somewhere else. I mean, if I wrote t to the qp up there, I'd have t to the pq up there, and I want everything to just appear once. So I write this infinite strip. And, a monomial ideal corresponds to some picture, looks roughly like that, where everyone who's in the ideal fits over here. Okay. But unlike in the case for Hilbert schemes of points in the plane, not every such picture corresponds to a monomial ideal, because of the thing I just said. As soon as this one is in, well, everything up there is in, but secretly some of the things up there, they were written down here. So there's some constraint. I mean, the constraint is that once you start dropping, you have to hit the bottom by q steps, after q steps. So now I just count those, and let me just say the formula which counts them.
And you're counting nested versions of that or something, right?
Yeah, so you count nested versions of it. But now, I mean, I'll just count it with a number of generators, and maybe I might as well, since I keep saying that, I might as well say that an equivalent way to write this thing, equivalent way to write that thing, is if you write C, P, and let's say like this, and K for Hilbert scheme, for when the ideal has K generators. That can be rewritten as A over Q mu minus 1 sum Q to the 2n, A to the 2m, 1 minus A squared K. Okay. So these things are just equal. Okay, so now on to the counting formula.
What do you do when you have to compute the whole Hilbert model?
You have to work harder.
Okay. These things aren't smooth, right?
No, they're not smooth. They're paved by affines, but of course, the paving is, I mean, you have to figure out the actual deformations with constant centigrade. And you can do it, but it's, I mean, we have some formula, but it's still in terms of some combinatorial data, and it can be computed in any given case. Okay, so the way you count these is I'm to count them column by column. And so I write, first of all, there's some arbitrary number of columns. So this Q is not that Q. Yeah, I better change that Q. Oh, Jesus Christ. Okay. Oh, these ones are P's. These ones are P's. Okay. So, this Q is the counting Q, I mean, the one that's in the... Okay, so there is some number of columns which are, have the full height. And each one of those contributes length 2m to your scheme. And then there are some number of columns which have the next less height. And each of those contributes q to the 2m minus 1. Except, as soon as you have one of them, you've picked up a generator of your ideal. So I write here 1 minus a squared. And also I'm going to put another variable, which I'll I'll put another variable down there. And, then it keeps going. So in other words, I write, and then at the front, I write the residue, so I put 1 over c to the m plus 1. This, of course, should have been not m but p because the height was p. And I write the residue at c equals 0. You see, this variable, it was insisting that the number of columns that don't have full height add up to exactly n. That was that dropping condition.
Out a particular.
Yeah. Yeah. And it turns out, if you analyze this series, you can see a bunch of other poles. If you move the residue over there, so move residues. You get Jones's formula for the HOMFLY polynomial. Of this source, not. I guess I call this M now. Okay, maybe I'll stop there.
Do you have any questions or
So, you're studying so the curves, the singular curve sits inside a surface, and you're looking at Hilbert scheme of points on the curve, which is lying inside the Hilbert scheme of points on the surface. And the surface is, Hilbert scheme of points on a surface is hyperkähler. Is this sub-scheme of the Hilbert scheme of points like Lagrangian or in one of those hyperkähler structures? It's kind of half-dimensional.
Yeah, I think so. And so Lagrangians always come from Hilbert schemes of points on curves.
Yeah, so can you...
I mean, I haven't thought of a way to use it.
More questions?
In this work by Kuka, Fenfield, and Rasmussen,
Yeah.
the categorification of HOMFLY, categorification, involved some open string BPS invariants.
Yeah.
Do you know if these moduli spaces have anything to do with?
No, you guys are supposed to tell me. I can't tell you. No, I hope so. I asked around, but no one's been able yet to give me a straight answer to that question.
Is there any three-dimensional round in order to consider Hilbert schemes on the curve?
So, there is something three-dimensional about the story that I've left out. HOMFLY, it comes with a partition. I mean, this whole time I've been talking about the HOMFLY and the fundamental representation of SLN. If you take other representations, then we think what you're supposed to do is take your singular curve and add another dimension and thicken it by this partition in the transversely, and then compute similar things. We haven't made that completely explicit
You're
yet.
adding two dimensions, right?
Well, one dimension was already there. You can thicken it in the plane. You can thicken it out of the plane.
So does this make sense at the singular point to thicken?
Yeah, I mean, there's a precise definition of this. Well, the precise definition of this is, this partition. You write f, 1, f squared, and here you write z, and then you get some ideal in f of z, and f is the function of
I
z.
see,
Yeah.
I see.
So there's some precise. So I don't know. I mean, anyway, that's more three-dimensional. I don't know.
Think this be very good.